Professor, what does ETH-MC2 really mean?
Emily asked, her brow furrowed with a mixture of curiosity and apprehension. She had always been fascinated by the mysteries of the universe, and this equation seemed to hold the key to understanding so much of what she had been learning. The classroom fell silent as everyone turned their attention to Professor Thompson, eager to hear his response. Professor Thompson smiled warmly, recognizing the spark of inquiry in Emily's eyes, a spark that had ignited countless scientific breakthroughs throughout history. He appreciated these moments when a student's curiosity could lead to a deeper understanding for the entire class.
Emily, that seemingly simple equation is one of the most profound discoveries in all of physics. It's a window into the very building blocks of our universe. You see, ETH-MC2 tells us that energy and mass are interchangeable. They are different forms of the same thing. This equation, proposed by Albert Einstein, revolutionized our understanding of the physical world.
He paused, letting the weight of the statement settle before continuing. The students leaned in, sensing that they were on the brink of a significant revelation.
It tells us that energy and mass, two things we often think of as separate, are actually deeply connected, two sides of the same cosmic coin. This means that a small amount of mass can be converted into a tremendous amount of energy, and vice versa. This principle is what powers the sun and the stars, and it's also the basis for nuclear energy. But how can something like energy, which is invisible, be the same as mass, which we can see and touch? Emily's question echoed the thoughts of many in the room. The concept was both fascinating and perplexing.
Emily questioned, her curiosity deepening. She had always been a keen observer, and this moment was no different. She wanted to grasp the full implications of what Professor Thompson was explaining. Professor Thompson, with a twinkle in his eye, launched into an explanation that promised to illuminate the magic hidden within Einstein's elegant equation. He began to describe how, at the atomic level, particles could transform into energy, and how this transformation was a fundamental aspect of the universe. He spoke of the experiments that had confirmed Einstein's theory, and the practical applications that had emerged from this understanding, from medical imaging to energy production. The classroom was captivated, each student hanging on his every word as they embarked on a journey through the wonders of physics. "Let's break it down," Professor Thompson suggested, grabbing a piece of chalk and writing the equation on the board. The classroom fell silent, every student's eyes glued to the chalkboard. The equation, ETH-MC squared, seemed simple, yet held profound implications.
E stands for energy, the ability to do work. Energy is all around us in the food we eat, the sunlight that warms us, and the electricity that powers our homes. It's a fundamental concept that drives the universe.
He pointed to the letter E, underlining it twice for emphasis. The students leaned in, eager to grasp the significance of each component of the equation.
M represents mass, the amount of matter in an object. Mass is what gives an object its weight, and is a measure of how much stuff is packed into it. From the smallest grain of sand to the largest star, mass is a key property of matter.
He circled the M, highlighting its importance. The students scribbled notes furiously, trying to keep up with the professor's explanations.
And C, what does C stand for? The students were curious, their minds racing to connect the dots.
Emily chimed in, her voice laced with anticipation. She had read about the speed of light but wanted to hear the professor's take on it.
C is the star of the show. It represents the speed of light, a constant that is crucial in the realm of physics.
Professor Thompson chuckled, enjoying the students' enthusiasm. He loved these moments of discovery and curiosity.
It represents the speed of light, a mind-bogglingly large number, approximately 300,000 kilometers per second. This speed is not just fast, it's the ultimate speed limit of the universe.
He went on, explaining how this constant speed plays a pivotal role in the equation. The students listened intently, their understanding deepening with each word.
What Einstein brilliantly realized is that this tremendous speed, squared, isn't just a random number. It's a fundamental part of the universe's fabric, linking energy and mass in a profound way. It acts as a conversion factor, revealing the incredible amount of energy locked within even the tiniest bit of matter. This insight has led to groundbreaking advancements in science and technology, from nuclear power to our understanding of the cosmos.
This equation, Emily, is the reason stars shine and why we have nuclear power, Professor Thompson explained, his voice filled with awe.
Nuclear energy?
Emily echoed, her eyes widening.
But how? Imagine splitting a tiny atom. When this happens, a minuscule amount of mass is lost. Seems insignificant, right? But that tiny bit of lost mass, multiplied by the speed of light squared, releases a tremendous amount of energy.
It's like unlocking the concentrated power of the universe itself, he added, emphasizing the magnitude of Einstein's discovery. This equation, he explained, was the driving force behind both the destructive power of nuclear weapons and the potential of nuclear energy to provide clean energy for the world. Section 4. Reaching for the Stars, Space Exploration, and Einstein's Equation. This section delves into the fascinating intersection of space exploration and one of the most famous equations in physics, E=mc², formulated by Albert Einstein. This equation, which expresses the relationship between mass and energy, has profound implications for our understanding of the universe and our ability to explore it.
Professor Thompson continued, his voice taking on an almost dreamy quality as he shifted gears. When we talk about space exploration, we're not just talking about rockets and astronauts. We're talking about the fundamental principles that govern the universe. EMC2 is one of those principles. It tells us that mass can be converted into energy and vice versa, which is crucial for understanding how we can harness energy for space travel. And it's not just about energy here on Earth. The same principles apply when we look at the cosmos. The energy that powers our rockets and spacecraft is derived from the same fundamental laws that govern the stars and galaxies. This interconnectedness is what makes space exploration so exciting and challenging. EMC2 is the key to understanding the vast universe around us. Space? It's a vast, almost incomprehensible expanse filled with mysteries and wonders. This equation helps us unlock some of those mysteries. For instance, it explains how stars shine by converting mass into energy through nuclear fusion. Without EMC2, we wouldn't be able to understand the life cycle of stars or the energy processes that occur within them. Emily asked, captivated by the conversation. So, does this mean that we could potentially use this equation to travel to other stars? Her eyes sparkled with curiosity, reflecting the wonder and excitement that space exploration inspires in so many.
Absolutely. The principles behind EMC2 are already being used to develop new propulsion systems that could one day take us to the stars. Imagine a future where humanity can travel to distant galaxies, exploring new worlds and uncovering the secrets of the universe. Imagine a rocket ship traveling at incredible speeds, close to the speed of light, Professor Thompson explained. At these speeds, the effects of relativity become significant. Time would slow down for the travelers compared to those left behind on Earth, a phenomenon known as time dilation. As it approaches this incredible velocity, its mass actually increases, requiring more and more energy to accelerate further. This is a direct consequence of Einstein's equation, showing the deep connection between mass, energy, and the speed of light, requiring more and more energy to accelerate further. This is why interstellar travel is so challenging. The energy requirements are immense, and we need to find efficient ways to generate and store this energy. He went on to describe how scientists use EMC2 to calculate the energy needed for interstellar travel. This involves complex calculations and innovative engineering solutions to make space travel feasible. The equation is not just a theoretical concept, it's a practical tool that guides our efforts to reach the stars, and to understand the mind-bending physics of black holes, where gravity is so strong that even light cannot escape its grasp. These cosmic phenomena challenge our understanding of physics and push the boundaries of what we know, where gravity is so strong that even light cannot escape its grasp. Black holes are regions of space where the gravitational pull is so intense that nothing, not even light, can escape. They are a testament to the power and mystery of the universe, and studying them helps us understand the fundamental laws of nature. Section 5, The Universe in a Grain of Sand, EMC2 and Particle Physics.
But, Professor, Emily interjected, you mentioned that even the tiniest bit of matter contains enormous energy. What does that even mean?
Professor Thompson smiled, delighted by Emily's insightful question. It means, Emily, that the world is far stranger and more wonderful than we could have ever imagined. He continued, explaining that EMC2 is fundamental to understanding the subatomic world, the realm of particle physics. He described how scientists use powerful particle accelerators, like the Large Hadron Collider, to smash atoms together at near light speed. These collisions, he explained, release immense energy, briefly recreating the conditions of the early universe and allowing physicists to study the fundamental building blocks of matter. Section 6. Fun with Physics EMC2 Trivia and Myth-Busting.
Now, for a bit of fun, Professor Thompson announced, a mischievous glint in his eye. Did you know that the energy equivalent of a small paperclip, if fully converted, could power a large city for a day? Emily gasped, astounded. But Professor, she exclaimed, I thought nothing could travel faster than light.
Professor Thompson chuckled. That's a common misconception, Emily. While nothing with mass can travel the speed of light, we can use EMC2 to understand what might happen as objects approach this cosmic speed limit. He explained that as an object approaches the speed of light, its mass increases infinitely, making it impossible to reach that ultimate speed.